All right, welcome to video 13. In this video, I'm going to be introducing a new method of proving that arguments are valid or that other logical properties are had by other sets of statements in SL. So the first thing we want to do is review the difference between syntax and semantics, right? Syntax is the study of rules for manipulating symbols without reference to any knowledge about what those symbols mean, right? So computers are syntactic engines. They are capable of manipulating symbols, for instance, in a PowerPoint, but they don't know what the symbols mean. They just follow rules. Semantics is the study of language, including the meaning of the parts of language. So the meaning of words, also whether or not individual sentences are true or false. What we've been doing so far with truth tables has been a semantic method of determining whether an argument is valid or a statement is a tautology, etc. And when we prove something, that something is a tautology, when an argument is valid using truth tables, we use the symbol in the lower left called the double turnstile, right? It's a semantic therefore. It represents, or we call it semantic entailment. Our new method of proving arguments valid is going to be syntactical. We're not going to take into account any aspect of meaning, and so we're going to use this symbol, the single turnstile, which is in red beneath the word syntax, in order to represent that one thing follows from another based on syntactic entailment. As it turns out, semantic and syntactic entailment both wind up proving the same things in SL, which is good. That's what you want a logical system to do. That doesn't always work out for other logical systems, though. So we've got two methods for proving things. The semantic method was covered in chapter 5, and that's truth tables, whereas the syntactic method, we're calling it derivation or proof, is covered in chapter 6, and that's what we're doing now. And as I said, these two systems turn out to be equivalent. Okay, so why do we need another way to prove things valid? Take a look at these two arguments. So P or Q and not P, therefore Q. Also, P implies Q, P, therefore Q. You can prove these using truth tables, and you may even want to pause the video and just do the truth tables here as a little exercise for yourself. So if you did the truth tables as a little exercise for yourself, you probably got this, right? So for the argument on the left, the P or Q is only false at the very bottom. Not P is true on the bottom two lines. So there are no lines where both premises are true and the conclusion is false. And the same is true for the argument on the right. There are no lines there where both of the premises are true and the conclusion is false. Now let's think for a second, though. If you knew, which we just proved, that P or Q and not P implies Q, would you really need a separate truth table to show this longer thing? C or parentheses A and B, comma, not C, therefore A and B. I mean, look at this. These actually line up, right? The not C, P or Q is basically the same as C or A and B. The parentheses mean that the or is the main connective in each of these. So for the sentences in the box, there is an or as the main connective for both of those. For the next two, you've got single sentences that are negated. And furthermore, they are identical to the left-hand side of the disjunction we saw on the right, on the left. And then again, the conclusion is the same as the other disjunct, right? So we've got the same main connective in both premises. The form of the argument essentially looks like what you see below. A or B, not A, therefore B. And here I'm using the script letters to indicate that these could actually be any individual, any sentence in SL. So for the top line, P or Q is what's playing the role of A or B, and you just substitute P for A and Q for B. In the second line, you're substituting a single letter for A, C, and then B becomes a longer sentence, A or B, but it works out to be the same, right? Now, these two sentences, these two arguments have different truth tables, right? And in fact, the truth table for the second argument is kind of long and a pain in the neck. But if we're doing truth tables, we have to do them differently. Well, what if we just had the exact same argument with different sentence letters? If you knew the P or Q argument, surely you wouldn't need a separate truth table for A or B. But, I mean, that's the way the truth tables work. You only do them for individual combinations of sentences. What we want to be able to do is say that any argument that has this general form is valid, right? So script A or script B, not A, therefore B. If you've got a disjunction and you negate one side of this disjunction, you can show the other side. And this is true no matter what you substitute in for A and B. Script A and script B. So what we need now is the concept of a substitution instance. Our argument scheme is above. Script A or script B, not script B, therefore A. And then all three arguments underneath are substitution instances of that. That is, you can get them by substituting different sentences in for the script letters up top, right? So you could get if you just put in A for A and B for B, you get the argument on the far left. The middle argument comes by putting in X implies Y for A and Z for B. The third argument comes in by putting in G and F for A and H and Z for B. But they're all essentially the same argument. So what we do in section 6.1 is we introduce our first two argument schemes. And we're going to call them disjunction elimination and conditional elimination. These are the two arguments that I introduced at the beginning of this. Now, the other thing we can do once we have decided that arguments that fit this scheme are valid is that we can start to string together valid arguments to make other valid arguments. So imagine you wanted to show this. Not L and not L implies J or L, therefore J. This actually can be done by breaking it down into two arguments that have schemes that we think are valid, and then stringing them together. So given the two premises in the argument as it sets out, we can infer J or L. And then given J or L and our original first premise, not L, we can get all the way to the conclusion J. So this is what we do when we do derivations, right? We string together arguments, we string together our basic rules that we have decided in advance are valid to prove other things. So with the thing we wanted to, with the argument we were just looking at, you would begin like this. You write your two premises on separate lines. Then you write want J. So that's the upper diagram there. You just add now one line beneath it to get the second diagram, and when that line that you have added there works by taking the first two premises and combining them using our rule of conditional elimination, which is one of the two rules that I just showed you, right? And then the bottom diagram is the finished proof. You add a fourth line, which follows from the two previous lines, lines 2 and 3, by disjunction elimination. So let's take a look at some of the homework problems. Okay, so for the first set of problems, you just need to identify when you've got substitution instances that correspond to the sentence form that was given in meta variables. And so I've put this into a Word document. It doesn't look quite that clear, but it's good enough. So the first example is just the sentence a script A and script B. So we're looking for sentences that can be formed by putting other sentences in for the script A and the script B. Line A is P or Q. That doesn't work, right? Because you've changed the main connective from an and to an or. But now look at the next problem. So here, the main connective was the and. You can zoom in, right? And down here, the main connective is the and. And then you've got, on either side of it, you've got the same, you've just got things that can be substituted in. So the A here can become A implies B. The B here can become C. So this is a proper substitution instance. We'll just circle it. So the next sentence is more complicated, but it sort of works the same way, right? In fact, it works exactly the same way. Let's get that there. So we can have, if we have script A, and we say that script A is equal to A and B, I want this in times, right? I'm sorry. Script A is equal to A and B implies B and A. Smaller, there, right? Then we can see that with this substitution here, A is the same as that. The and matches. And now we just need something for the B, and the B is going to be the same too. Well, we can make the B match as well. So we can say that the B is the same as, why don't I just cut and paste and make my life easier? That, right? And then you can see because of those two substitutions that this is a proper substitution instance. The same is true for D. D is a proper substitution instance because the main connective in each is an and so the left side is the A and the right side is the B. E is not a proper substitution instance because the main connective this time is just a conditional, so that doesn't work. So that's a simple case because we're just looking at a situation where you've got a single connective. If you've got two connectives, like in number 2, things are a bit more complicated, but what you need to be able to do is just have all the connectives that are in your sentence frame also be in the substitution instance in the same order, right? So for the first one, you can see you've got a negation, and then a negation, and then you've got an and then an and. So that works. P is A and Q is B. We'll put a circle there, and then I'll just put a little note to make this clear. That script P make this smaller and red. Script P is equal to A, and script Q is equal to B. All right, now what about the next one? For the next one, it says not A and A. You might think that's not allowed, but it is, because it is perfectly legit to substitute in the same sentence letter for both of the script letters, both of the meta variables. So if we say that P is A and Q is A, we get the sentence above, and that's totally okay. In fact, there are going to be times when you need to do that. C, on the other hand, doesn't work because the parentheses are gone. In our sentence frame, the main connective is the negation. But in C, the main connective is the and, so that doesn't work. And then the other one from this batch that is a substitution instance is D. Oops. Right? And that just comes from substituting in those longer sentences for P and Q. E is not a substitution instance because the and has changed to a conditional. So that's how you do the problems in that set. And that's sort of the basic skill, is recognizing substitution instances. If doing derivations was playing basketball, then recognizing substitution instances is like doing a layup. It's just a basic move that you have to practice all the time. Okay. We can skip the rest of those. I can skip them. You can't. I want to show you C goes the other direction. That's pretty straightforward. You don't need to see that. But I do want to show you about identifying substitution instances for modus ponens. Okay, so that is, we're calling it conditional elimination, arrow E. So first thing to do, I think, is just to remind ourselves what the argument scheme is for this. We'll make these all script letters. And like that. And then we'll just grab a line from over here. Ugh, I hate it when it does that. I tell you what we'll do. Well, we will we'll draw a fresh line. There we go. That'll be our line, right? So in order to identify cases of conditional elimination, we just need 3 sentences in a row that are all substitution instances for these sentences. So 1 is not a substitution instance. Because although the first sentence matches, the first premise matches, the conclusion, the second premise and the conclusion do not. Number 2 is also not a substitution instance, right? Nor is number 3. And hopefully you can see why this is the case each time. For number 2, you don't have a and. You don't have a conditional. You've got an and. For number 3, you're missing one of the premises. Let's see if we can put that there. Yeah. 4 does work, however. The spacing on this is all. So I transfer this from PDF to Word, and the formatting got kind of wonky. But I think you can see. Let's just move that there. And then here, and hopefully, no, it's being difficult. There. Oh, and this one doesn't work either, because check this out. I nearly fell for my own trap. The first one is D implies E. As A implies B. But the second line should be the antecedent of the conditional. So this should be D rather than E. So this also doesn't work. The only one that's a proper substitution instance is this one here. Because that's A, that's B, that's A, that's B. So if we go over to our answer sheet, you can see that only the final one is marked as, in this case I marked it modus ponens, but it's arrow E, conditional elimination. Okay, I'm going to do one more problem and then you're going to be on your own. So right now I am just going to fill in the blanks for this problem set to show you how full derivations work. And then basically from here on out, the rest of the semester, we're just going to be doing this kind of derivation. So you need to learn to do them. All right. So these are our premises. This is the conclusion. We want somehow to get from these premises to this conclusion. And these are all the steps to get there. The first step is to infer W. Where do you see W in the premises? Well, there's a W up here, but that's not actually where we want it. We don't have a rule that would let us get that W from that line. Really, we want to use the W that is down here. So what we can do is we can say that this is and elimination on line 2. Right? Then once you have the W, you can get the not B, and that's conditional elimination using lines 1 and 4. And that is happening because if you put this line together with this line, you get an instance of the argument form conditional elimination with not B as its conclusion, right? So let's just give ourselves some space down here and show you what that looks like, right? So I copy one line, I copy the other. I just cut and paste line 1 and line 4, and you can see that it matches the scheme for conditional elimination with not B at the end. We can underline there, right? That is just the argument that we're using. Once you have not B works with this line here and or elimination to get you J and K. Oops. So this is or elimination, lines 3 and 5. And then K just comes with and elimination on line 6. And so that's how you fill in that sort of problem. All right, I want to end by showing you some of the significance just of what we're doing, why I'm teaching you to do these things. Because the science of logic is old and powerful. So actually what you're looking at here is some math homework from 4,000 years ago. The tablet in the lower right is known as Plimpton 332. It's from ancient Mesopotamia, and it looks like someone's math homework from somewhere around 1800 BCE to maybe 1650 BCE. And what they're doing here is solving the Pythagorean theorem repeatedly. The Babylonians, the ancient Babylonians in Mesopotamia, knew Pythagoras' theorem. And they've got tables like this that show triplets. Actually, this might be a reference table rather than a bit of homework, but we also have homework from the same period, including word problems, funnily enough. But so what you see here is that the Pythagoreans understood the truth. The Babylonians understood the truth of the Pythagorean theorems, but they weren't able to, they didn't understand why the Pythagorean theorem worked. At least we don't have evidence that they did. Later on, though, people do start to understand why Pythagoras' theorem is true. So Euclid, the ancient Greek geometer, was able to prove the Pythagorean theorem using a method of proof that is what ultimately comes down to us in history as the same sort of thing we're doing now. That is, you take some basic rules of inference, and then given a starting point, you can build up more and more elaborate theories. And the goal, actually, since Euclid's time, one of the things that people have tried to do is axiomatize arithmetic. That is, create a system of proofs from self-evident premises of all the statements in arithmetic. So Euclid's Elements, books 7 through 10, deal with arithmetic, and he's able to prove things like there are an infinite number of prime numbers, or that irrational numbers exist, and that all numbers have a unique prime factorization. So he is able to prove things about math using derivations, using a system of derivations that then encompasses the whole book. And so that's what we're beginning to play around with here, is a system where you start out with a few basic premises, and then you are able to prove many more logical truths.